Alright, this is all charged up. This is a video lecture on charge and what charge is and everything else. The quote that we have is, "Words can have no single fixed meaning. Like wayward electrons, they can spin away from their initial orbit and enter a wider magnetic field. No one owns them or has proprietary rights to dictate how they will be used." And so this lecture is going to be all about electrons and their charge. So the goals for this presentations that you should be able to demonstrate the relationship between our protons and electrons and charge, identify the different methods of charge, so how things become charged, apply the law of conservation of charge, and calculate the charge using the formula Q equals Ne. So, what we should have already known is that charges can be made from the Van de Graaff generator. We could look at that and see that demonstration. That positive charges have more protons, so positive charges have more protons than electrons. Negative charges have more electrons than protons, and charge can be transferred between objects. So if you've ever been shocked by somebody walking on some carpet in your socks, you have felt charge and the transfer of charge. What we should have learned from the lab is that rubbing an object on rabbit fur or in your hair can charge the object. That positive objects are attracted to negative ones, and neutral objects are attracted to both positive and negative ones. And so we should have learned this from the lab. We should know that positive objects are attracted to negative ones just from our previous knowledge and from the lab. So Thales, the first person we're going to talk about, is a Greek philosopher and mathematician. He was famous for measuring the heights of the pyramid, and he was the first recorded static electricity in amber. And so he was the first person to kind of talk about charge, electricity, and those types of things. Got us kind of thinking in the right direction. So looking at what charge is, there are two types of charge, only two types. We have our positive and we have our negative. Now our positive charges is the number of protons exceed the number of electrons. Now we don't really ever lose protons. We can't lose them, we can't gain them, and so what happens is it's the transfer of electrons. Okay, so we'll have the protons will be larger. So basically, if you have a positive charge, you have lost some electrons. If you have a negative charge, on the other hand, that means the number of electrons exceeds the number of protons. So basically, you have gained some electrons if you are negative. If you're positive, you have lost some of your electrons. And this should kind of bring you back to kind of your chemistry days when we talked about that. Now, our charged objects. It is possible to transfer electrons between objects. The thing here, and this is what I was talking about back in this one, that only electrons are transferred, never protons or neutrons. So we can transfer electrons between objects, but only the electrons move. None of the protons, none of the neutrons move. Only the electrons move. So if we are positive, then basically we have lost an electron. If we are negative, then we have gained an electron or done something to become more negative. Now, Thomson's experiment, when we're looking at Thomson, he studied the cathode rays moving towards a positively charged plate. Now, this is basically Thomson led to the discovery of the electron. And basically what happened is cathode rays, they kind of led to the earlier televisions. And basically what happens is it's this charged particle, and basically it's moving towards this positive end over here. And what we see is that it created this beam of light, and basically this cathode ray, we saw this ray moving through it, and these two plates sitting right here, one was positive and one was negative. And what Thomson realized is that they would be attracted towards that positive plate, and so what was moving had to have this negative flow. So this part right here was going to be our negative, and what they figured out was basically that that was an electron. It was determined to be an electron. Now, the protons and electrons in charge, basically what they have in looking at these is that protons and electrons are both going to have equal magnitude of charge. So it's, remember, magnitude, it just means that it's a number. And so it's 1.6 times 10 to the negative 19th coulombs. And so your electrons are negative, so they'll have a negative 1.6 times 10 to the negative 19th. And then your protons will be positive 1.6 times 10 to the negative 19th. And so basically in a neutral atom you both have both positive and negatives, equal amount of protons and electrons, and so therefore your overall charge will be neutral. Big difference between electrons and protons. Electrons are incredibly small. Okay, we see that protons are 1.67 times 10 to the negative 27th kilograms. And then we have 9.11 times 10 to the negative 31st kilograms, which that's a huge difference in size. And so protons are much more massive compared to electrons, but even though they have different masses, they still have the same charge, the same magnitude of charge. So let's look at an example. It says, which subatomic particle has the greatest magnitude of charge to mass ratio? So it's charge to mass. Now they both have, both a proton and an electron has the same charge. It's at 1.6 times 10 to the negative 19th. Okay, we're looking at that compared to their mass. Now we know that an electron's mass is incredibly small. So if a really small number is on the denominator, that means our ratio is going to be a very big ratio, very large ratio in comparison to that of a proton. So an electron is going to have a very large charge to mass ratio compared to a proton. Okay, looking at the next one, it says a neutral object becomes positively charged. Describe the movement of subatomic particles that allows it to become charged. So it becomes positive. So if something becomes positive, that means it's lost an electron. So we can say that some of the electrons were taken away from that object, and when it was taken away, this sphere became positively charged. Okay, so let's look at the different types of transferring of charge. The first one is charging by conduction. And so basically what happens is when you're charging by conduction, it requires direct contact. It's the main thing here, direct contact between two objects of different charges. It works for conductors only. This is the main thing, that it has to be a conductor for it to work, and it has to have that direct contact. Then we have charging by friction. You can see this done by a Van de Graaff generator. Basically it moves a piece of material through it that causes that friction. It's work done by friction to physically remove the electrons, and so they're moving the electrons, and you can see that it travels through, and then the charge is dispersed and the electrons flow through it. It's similar to conduction it requires that direct contact, but they're physically removed by that friction that it's caused, and that's the main difference. Then you have charging by induction, which is the transfer of charge with no direct contact to the charged object, and it can be used to produce an oppositely charged object. And so the induction, basically what we're happening is that you have no direct contact with it, but basically you are pulling that charge, and that charge can be dissipated. Polarization is another way that we can do it. Generally means there's no net charge, and it's going to be zero. The objects are divided so that the charge moves to the opposite and negative halves. And you can think of it this way. We've talked a lot about polarization in chemistry. It's the fact of that you'll have a positive end and a negative end to it. Neutral objects attracted to the charged ones, and so basically what we see is they both have positive and they both have the negative, but it's just polarized in the fact that it's going to be negative on one side and positive on the other. And that's basically what polarization is you have positive on one side and negative on the other. Then you have conductors, that metals have free electrons in their delocalized d orbital. What this means is basically in chemistry we talked a lot about the free or sea of electrons, and they're free flowing. And basically what metals have and why they are good conductors is that they are able to let electrons flow and allow electrons to move through with relative ease. Gold is a really good conductor. Gold's used a lot in space equipment just because it doesn't corrode or anything like that, but also because it is a great conductor of those electrons, and electrons move very easily because they have those delocalized d orbitals. Basically they're not attached and they just free flow. An insulator would be electrons that are tightly bound to it. Doesn't allow electrons to pass through it very easily, and so since those electrons are very tightly bound, they're very held together, they don't let other electrons flow very well. And so they're very good insulators, so they stop that flow and they keep that from happening. Glass is a really good electrical insulator because it stops that flow. Okay, let's look at an example. It says that semiconductors are necessary for modern electrons. Speculate on how electrons move through semiconductors. The main thing here, semiconductors are temperature dependent resistors, so their ability to hold onto their electrons depend on the temperature, and so as the temperature changes, their ability to hold on to it, that it changes as well. And the main thing here is the reason why you want your semiconductors is so that you can vary the charge, meaning they can flow through at one time and then not flow through at another. And when you can control that, well, you can use it to turn and turn off switches and things like that in computers, and that's the main thing. B2 is superconductors provide absolutely no resistance to electrons moving through them. Speculate on what makes an object a superconductor. So when we're looking at what a superconductor is, superconductors exist at very cold temperatures. And they do not hold on to their electrons at all. And because they do not hold on to their electrons at all, they're able to allow charge to move through with absolutely no interaction with it. And so that charge will move completely through with absolutely no resistance to it, which allows it to transfer that charge very effectively. Alright, let's talk about the law of conservation of electrical charge. It states that the total amount of charge in a system must remain the same. So the example is if a total charge of 0 for a system is 0 for a system, then two objects can have any charge as long as the total number of the two is 0. So as long as it's 0, then that's fine. We'll use this example over here. If we're looking at the system, we have negative 12 and plus 4, which gives us an overall charge of the system of negative 8. So as long as the overall charge of the system is negative 8, we're good. So as these two come together, what happens is we have this negative 8 total charge that's kind of separated between the two. So we have negative 4 and we have negative 4, which still adds up to the law of conservation of electrical charge, because the total charge of the system would have been negative 8. And looking at this, let's look at Benjamin Franklin. He distinguished between positive and negative charges. He was the first to explain the law of conservation of charge. He discovered that lightning is electricity, and he invented the lightning rod. Now, the Franklin experiment that everybody sees is that he connected a key to a kite, hung it up in the air. Didn't actually happen. So Franklin already knew about grounding and did not hold the key as shown right here. But notice the loose hair becomes charged and stands up. We saw that on Van de Graaff generator. So let's look at an example. Example C1. It says that two spheres of -4 and +9 elementary charges are touched and then separated. Describe the magnitude of charge for each after they are separated and the flow of charge necessary to reach this overall charge. So when we're looking at this, our overall charge of the system, +9 +4, that's going to give us a +13 for the entire system. So when we're looking at this, so you have 13 in the two spheres, so you divide it by 2, and what it equals is basically you can't have half charges, so you're going to have something that's going to have a +7 and something that is going to have a +6. There's no really way to distinguish between which one is which, but basically you're going to have two spheres, +7 and +6. If this was 14, then obviously it'd be 7 and 7. But if it's an odd number, like 13, then we see that one will be greater than the other. And we really can't tell the difference between it. Now, what happens is the electrons flow from the +4 sphere to the -9 sphere until it reaches that +7, +6 for overall charge. Because when we're looking at this, the +4 has more electrons than the +9, so the electrons will flow through to the +9 until it balances and we get that +7, +6. Looking at another example, states that a single object has a charge of 5, and that is microcoulombs, before splitting into two different pieces. The first piece is measured to have a charge of -2 microcoulombs. What is the charge of the second piece? So, law of conservation of charge, it all has to add up to 5 microcoulombs. And so what we'll have is, since the overall charge is 5, and then we know that one piece, it has to be -2, they both have to add up to 5, so basically we have, well, what is x? So we solve for x, and x will give us 7. So if one piece is -2, the other piece has to be +7, so that it keeps that charge of 5. So let's take this back to chemistry and talk about charge that we found in chemistry. Now, we already talked about and said that protons and electrons each have the same charge value of that 1.6 times 10 to the -19th coulombs. And basically in chemistry we talked about the fact that we had oxidation numbers. So we had that positive or that negative oxidation number. And we talked about the fact that in an atom that those electrons can be transferred, that they can be gained or lost depending on what it needed in the atom. Now basically this positive, these oxidation numbers, the plus and the 2-, these values tell us how many excess protons or electrons that there are. And so we can use this to calculate out charge in physics. And look at that SI charge. And the equation that we have for it is Q equals NE, where Q is the total charge. It's the standard unit of proton-electron differential in an object. So it's measured in our coulombs, and basically it tells us the overall charge. And it is a qualitative, measured by a qualitative electroscope. N would be the number. It's the number, and this is important here, of total protons minus total electrons. And so what we have here is that we know that one proton and one electron, that they'll balance each other out. So there's no difference in charge. So what we're looking at here is that it's a total number of protons minus total number of electrons. It's the difference. We measure this by just counting, and then we have our fundamental charge of our E, and that should be a lowercase e, and it's 1.6022 times 10 to the -19th, and it is calculated. So let's look at an example that we have, example D1. What is the charge of 40 grams of doubly ionized sulfur? So what we're going to have to do is we're going to have to take this from 40 grams of sulfur and take it into, we're trying to find the charge. So we're trying to find Q in our equation. Q equals NE. So we're trying to find Q. We know the overall charge of what we're going to get is that E value is we'll just say 1.6 times 10 to the negative 19th coulombs. We know that value, we know that number. So all we need to do is we have to be able to find our N. Okay, to find our N, we need to take it from grams into moles, and then moles into atoms. And then for every single atom that we have, it's doubly ionized. So we're going to have 2 of our electrons per atom. So to do that, to go from 40 grams into moles, it's 40 grams of sulfur. So all we do is divide by the molar mass. So 32 grams of sulfur is 1 mole of sulfur. And then we look at it in 1 mole, we'll have 6.02 times 10 to the 23rd atoms. And in every single atom, we will have our 2 electrons. And so we multiply all this out and we'll get an answer right around 1.5 times 10 to the 24th electrons, and this is our N value, and that will go in right here. So we'll just multiply our 1.5 times 10 to the 24th electrons times our 1.6 times 10 to the negative 19th coulombs to get an overall charge, or Q, of 24,880 coulombs, and that will be our answer. Alright, so let's look at another example, example D2. It says, what is the charge flowing in a sheet of gold if we have 2.0 times 10 to the 13 excess electrons? So they're in excess. That means we have that many more electrons than we do protons are conducted into a sheet. So what we're looking for is we're looking for charge. Our equation is Q equals RNE. Okay. And so basically what we're looking for is Q. We know that E is 1.6 times 10 to the negative 19th. And so therefore all we need to have is N, which we have right here. So all we would do is go Q equals N, which is 2.0 times 10 to the 13th. That is our N. And times our charge of 1.6, the elemental charge of an electron, 1.6 times 10 to the negative 19th coulombs. Multiply those two things together and we will get an answer of right around 3.2 times 10 to the negative 6 coulombs, and that will be our answer. Example D3. It says determine the number of excess electrons in a negative 1 coulomb of charge. So here we have Q equals RNE. Here we have charge. We know what E is. It's always the elemental charge of an electron or a proton. We're searching for N. So if Q is negative 1 coulombs equals N times our E value, which is 1.6 times 10 to the negative 19th. Since it's electron, it is negative, and so therefore that's coulombs. So we divide both sides by negative 1.6 times 10 to the negative 19th, and we get N, which is the number of excess electrons, which should be right around 6.25 times 10 to the 18th. And that would be excess electrons.